All right, we should be streaming for WorldCon office hours, so everyone welcome to WorldCon office hours. I had some technical issues yesterday. I've been really having bad internet. Connection this week. Let's see how far we can get. Hopefully we can have a full hour of office hours. Apologies for yesterday. And two things. Someone talked about the kernel trick, and I was just building up to that. The kernel trick. But then things didn't work out. Things did not work out. So I believe we left off with Q2. We had this truncated SVD model that didn't do so well. So I'm going to go ahead and do kernel, restart and clear output. And let me go ahead and run those cells selectively. So cell run all above. Run that cell there. Why not that one? Why not that one? Right, it had the truncated SVD. Yeah, not fitted error. Because I probably had to train. I don't know why that's even there. So I'm going through the fitting process of the truncated SVD, so we can kind of get back what we had before. I see Suleiman here, Renato, and Mickey. Plus, let's see your face in large view for seconds. Yeah, it looks like my screen's a little smaller. It always does that. I don't know why my streaming software tends to change the webcam view, the webcam size from time to time. I'll make that adjustment right there, so it's a little bigger. I see Esau is here. Welcome, Esau. And all right, that was quick to train. The best params is alpha 1, which is somewhere in the middle. Look at the score. Perhaps not so great as I give it to the grader. And I think someone asked yesterday, hey, can we see the predictions, right? We can see the predictions. Right, nothing too exciting will come out of that. But I can do nonetheless. I actually get an error here, value error. Number of features of input must be equal to or greater than that of the fitted transformer. Not sure what's going on there. Okay, let's see there. 100 components. Normalize. I'm not sure. Yesterday this ran. Not sure what's going on here. Number of features of the input must be equal to or greater than the fitted transformer. So let's see what error it's pointing to. Column transformer. Oh, I know why. Because we've got to strip out all the unneeded fields and idiosyncrasy of the column transformer, which is fixed in the newest version of Python. Of scikit-learn, sorry. So let's try that one more time. Pass to the grader, and let's see what we get, and can make those predictions. I see someone has a question here. It says, hi, I was wondering if there's a deployment part of this course. I believe the last set of lectures talk about how you can deploy to Heroku, and how you can create a, you train a machine learning model, you save it to disk, and then you can use it to, and then you deploy it out to Heroku. So there are some videos in week 8 about that. So at the very end, a deployment piece. Nothing too fancy, nothing too elaborate, but we do cover that base there. And here we have our prediction back there. Not so great, but oh well. We do truncated SVD, and we can make predictions with our data if we like to. So there's some predictions. Right, we make it a train for a regression from values 1 to 5, so it makes sense that we get values from about 1 to 5. Of course, they're not going to be so great. We use the truncated SVD, really hampered our performance. So we can probably just knock that out. Now I don't like the level of verbosity. It's just too much verbose. So let me just go ahead and knock out the dim reduction. Comment it out. Let's see how well that does. someone did ask about the kernel trick, so I do want to talk about that. That was one of the things I was building up to yesterday, this idea of a kernel trick. Now with SVMs, and I'm not sure if we've given you the lectures of SVMs yet. I could be wrong. I can easily look that up. We go to Control Panel, and I go into Video Links, and I do Control F, Support. Well, no support. SVMs, no SVMs. So we've yet to give you those lectures about SVMs. We've yet to give you those lectures on SVMs. That is probably all of next week. So I will explain the kernel trick for today. And you might be wondering, what's this kernel trick all about? Well, I don't want to give away too much because those are in the lecture videos. But I want to mathematically show you the difference between using a kernel and not using a kernel, or using the kernel or explicitly transforming your space, so we can get a great appreciation of this kernel trick when we get there. Okay, the math is tricky. Yes, the math at SVM is SVMs are very math heavy. SVMs are very math heavy. Someone is saying they're wondering if there's audio issues. Anyone? Am I going through? Am I going through properly? I just want to make sure that it's not on my end, so I can get some confirmation whether I am going through properly. That would be good to know. Okay, no problem there. Thank you, Renato. So maybe it's something on your end. Unfortunately, right at. So I don't want to spend too much time about the math of SVMs, especially since you haven't formally seen those videos. But so next week, once you've seen those videos, we can talk a little more about the math of SVMs. But in the derivation of support vector machines, we have to take the dot product of two vectors. We have to take the dot product of two vectors. At some point in the math of SVMs, we take the dot product of two vectors. Now, one of the things that we know, sort of a separate issue besides this dot product, is if we create new features, we are more than likely able to get a better model. Generally speaking, if we add more features, we might end up having a better model. Of course, we got to be careful. There's always overfitting lurking in the corner. But generally speaking, we like to add features because it will help out our model's tasks for predictions. So one way we can create new features is we can do some sort of polynomial terms. We even have a polynomial transfer in scikit-learn. So let's say we have a 2D vector. Let's have a 2D vector. I'll call it v1 that has components x1 and x2. And I could explicitly transform this vector into a higher dimensional space. So those new features are x1 squared. One set, this is an example of what type of transformation I can perform. And this is getting a little bit in the way. Let me just erase this here. Getting in the way what I've drawn here, so I'll just circle this here. Right there. So I could apply a transformation and expand this to a space of x1 squared, a space of the square root of 2 times x1, x2, and finally x2 squared. So I could take this vector, x1, x2, and transform it to a higher dimensional space where these are the new features. And I can do the same thing with v of 2. I have a second vector v of 2. And since I already use x, well, this is v, any generic vector v. And then I can have v of 2, which is a1 and a2. And I have v1, which is b1, b2. This is a of 1. Let me just erase some stuff there. So I have a generic vector v of x1, x2. And I want to apply a transformation to go to a higher dimensional space of x1 squared, square root of 2 times x1, x2, and x2 squared. Let's not worry about why this dimensional space, right? Why x1 squared, why square root of 2, x1, x2. This is purely an example. This is purely an example of taking a two-dimensional data set and project into a higher dimensional space, a three-dimensional space, that hopefully we can do a better job of making predictions there. And I have two instances of my v vector, v1, v2. So v1, b1, b2, v2, a1, a2. And this is what I have here, my curse of dimensionality. So one thing I can do is in my equation for the support vector machine, in the mechanics of how to train a support vector machine, I have to take the dot product of my vectors. So let's see what happens if I project my vectors first to the higher dimensional space and then take the dot product. Let's go through that math of the step of taking my data, transforming it, and taking the dot product. So if I carry that out and I were to project this to a higher dimensional space and I do the dot product, I will have a1 squared times b1 squared plus 2 a1, a2, b1, b2 plus b1, b2 squared and a2 squared. So this is a math if I were to project my two vectors into three-dimensional space and multiply them, take the dot product. This is the expression I have. Any questions so far? I haven't done the kernel trick just yet. I'm showing you taking data, projected to a higher dimensional space, then taking the dot product. And this is the expression I get for those two vectors. See a question here. When using polynomial features, say for degree 3 for 3 features, how do you make sure sense of the regression coefficients in order to understand the importance of the contributions? So I see the question here. Well, okay, well I do polynomial features, so what was what, right? What was what? It's a little hard to track. And I think what I'll do there is I'm going to put a pin on that question there because I want to demonstrate that with the notebook. I want to demonstrate that with a notebook, or going through notebooks, some sort of live coding, but I will get to that today in office hours. I think it's a good question you bring up there. I'll finish up the kernel trick, and then we'll look into the good point you bring up there. So do remind me to make sure I don't leave office hours without talking about it. Other questions people have? So I'll summarize what we did. We took two vectors, we projected them to a higher dimensional space, and we took the dot product. That projection to the higher dimensional space might be costly computationally. We go from a 2D to 3D, which is okay, right? Only one dimension. But imagine we have lots of features and lots of higher dimensions. It can be computationally intractable. Well, what would happen if I take the dot product of my vectors in the original space and then run that scalar product through a kernel or through a function? Right, let's see what happens if I take my vectors v1 dot v2 and then run them through a kernel. And this kernel can be expressed as u squared. A kernel that simply says square the scalar. I take the dot product, I get a scalar. Dot products of vector scalars, right? We saw that in Unit 1. So why don't I take the dot product first, run it through the kernel, and let's see if we get the same result. Because this trick is going to save me from explicitly transforming to the higher dimensional space. So let's take the dot product of v1, v2. So I take the dot product of v1, v2, and I have a1, b1 plus a2, b2. And if I square this, well, I can do the FOIL method, a1 squared, b1 squared, plus 2, a1, a2, b1, b2, plus b2 squared. Isn't that the exact same thing I have over here? Aren't these two things the same thing? So what we observe is that I can get the same effect of an explicit transformation to a higher dimensional space and perform the dot product with taking the dot product first in the original space and running that scalar through a kernel, through a function. And this is called the kernel trick. It's a lot easier to work with a scalar as opposed to a vector. And if I take the dot product in a lower dimensional space, it's computationally easier to perform. So this is the kernel trick. Questions about the kernel trick? A2, did I mess up somewhere in the math? Right, it's a little hard to see, but those are 2's right there. Oh, I forgot a term, right? Oops. Forgot the A2 squared, B2 squared. Forgot about that. Thank you. Other questions people have, other things people want to point out. Okay, do let me know. I think I'm going to go to the point that Vicky brought up. I go to control, go here, let's say, go here. My server, data course, office hours. Let's open up a new notebook. Okay, so let's go and import some data. So surprise, surprise, we're going to import the California housing data set. So I can say fetch California housing. A couple other things we're going to import, like pipelines. We're probably going to use a pipeline. Let's go and import it. From sklearn, pre-processing, probably import a standard scalar. From sklearn, pre-processing, let's import a polynomial features. And from sklearn, a linear, let's import ridge. And let's see, from sklearn, also let's do import a train test split. Get in the habit of importing grid search and train test split, right? Always want to do a train test split. So let's get the data. Data equals fetch California housing, and X is data data, and Y is data target. And I can form a train test split. X train, X test, Y train, Y test, train test split, X and Y. Test size 0.2, random state 0. I think it's, okay, that worked out. I always forget if it's test size or test split. And that worked out. Let me create my model. My model will be, first I'm going to scale, scalar, standard scalar. And let me go ahead and have the poly features. So poly features, polynomial features, let's say degree 3, right? Degree 3, why not? And include bias false. We're not going to include the bias because that will be included in my ridge model by default, and I can say my regressor will be my ridge model. Let's not worry about tuning the hyperparameter for the moment. I have a 3-step process: scale, poly features, and ridge. So I can say model fit on X train, Y train. Got a name error because it's have a typo. There it is. Look at my model. And now I can do things like, hey, look at the coefficients. And here are my coefficients. The learn coefficients. Quite a few of them. Right, quite a few of them. Shape 164 coefficients. And now the question is, well, before, if I didn't have polynomial features, it was a lot easy for me to understand which coefficient belongs to which feature. But now that I'm doing these polynomial features, I'm going to lose track of what those are. I'm going to lose track of what was the most important features. What was a composite, right? Was it x1 squared plus x3? What was that? Well, let's look at my polynomial features, which was step 1. And let's actually see the attributes I have access to, right? So I can say for attribute in the dir of this function, if adder -1 is equal to an underscore, I know that things that I only know after I've been fitted end in an underscore. And I get a syntax error because it should be a comparison. And let's see, I'll probably have a double condition. Don't want those special methods. And not equal to underscore. And I have a couple of these features here, these attributes that end in an underscore. And which of these might be useful? So I have n features in. Let's examine that. This probably tells me how many features came in. 8 features. Well, let's make sense of that. Right, x train, shape. Yeah, 8 features. Okay. Well, let's see n output features. It's probably going to be what I observed before, 164. Again, name error because I forgot to say model 1. Attribute error. N output features. Probably have a typo. N output features. And it's probably, if I can copy that and paste it there, maybe that'll fix my issue. 164. Right. We observe that in the output data. 160 in the coefficient. And now let's look at powers. Okay, well this is a little weird. Okay, look at this powers attribute, but this might clue me in. This might clue me in what I'm working with. Well, let's look at the shape of this. What is this shape? Well, it's 8. It's the shape of 8. Okay. So what this probably is telling me, if I take a look at maybe the first, all the rows, all the columns in the first row, maybe this is telling me about the powers that were used to construct that feature. Let me verify that. Powers, shape. Powers. So what this might be telling me is that what ended up being feature 0 was the feature 0 to the first power. The original feature 0 to the first power. So let's kind of verify that. If I choose, let's say, 1, 2, 3, what this is probably telling me here is that this represents feature 0, 1, 2 times, so this is feature 0, 1, 2, 3, 4, 5. So feature 5 raised to the second power. That's probably what that is. So feature 123 is this new feature. Well, let's kind of prove it to myself, right? Let's prove it to myself. So I'll say model, and I'll take a slice, and I'll say transform on X train. Look at the memory usage. Whew, getting close there. Then I can say, well, did my transformation. Let me look at what just so happened to be one of those values. So this is the value for row 0, attribute 123. Well, I think it's feature 2, old feature 2 times feature 5 to the squared. Well, let's prove it to myself. I do X train, and I take the 0 row, and I think it's feature 2 times X train, row 0, and feature 5 squared. I don't have the same answer. Because of the scaling step, right? It's scale. Okay. So let me just go ahead and get that scaled version. It's a model. And I can say transform. And now I can try it out. Take row 0, take column 2, times row 0, column 5, squared power. And I get the same answer. So it looks like the way I can determine the compositions, what made up those new features, is for my trained polynomial transformer, my polynomial features, has a attribute called powers, where the number of columns are my old features, the number of rows represent each new feature. And the values tell me that new feature was created by feature 0 raised to that power, feature 1 raised to that power, feature 2 raised to that power, and so forth. And I proved it to myself by looking at the directions it gave me, so to speak, and I got the same answer. So that's how I can determine that. Questions we would have, follow-ups here. Okay, all right, good to hear, Mickey. All right. Okay, now my kernel is, I'm getting a little memory. So I'll save that. Let me go ahead and close out that notebook because I'm running deadly close out of memory. Can you repeat line 24? Line 24 in the notebook I had? Did I shut it off? I can open that again. Okay, what about that line? So this, let me reiterate. This tells me, right, this here, this tells me how feature 123 was created. In other words, the powers used to create the new feature based on the old features. So this has one, so that means that this feature 123 is x0 to the 0 power, x1 to the 0 power, x2 to the first power, x2, x3 to the 0, x4 to the 0, x5 to the 2. So you can think of it as a mapping instead of directions that tell me how do I go from those old features. So how do I construct, how were the new features constructed? Because if you recall with polynomial features is that I create new features based upon multiplications of my old features raised to some power. And this here tells me that this feature 123, it was composed, this is the powers of those features. So 0, 1, 2, 3, 4, 5, 6, 7. Any follow-ups? If you need to watch it again, no harms there, right? All right, cool, no problem. Anything else we want to bring up while we're at this point here? Okay, all right. I'm going to go ahead and close that chapter. I'll download that and I will make sure I shut it down just in case, because I'm kind of low on memory. All right, so let's go pivot back to the NLP mini project. And now I got to construct a bigram model. So things are going to get a little bit tricky here. So for this bigram model, what I want to go ahead and do is, okay, well, let's add some additional features. Previously, we were creating features purely on words, purely on single words. But now I want to create more features. I want to include bigrams. So previously, I was trying to predict the rating of a review by using the words like terrible, great, so-so. Well, so-so is 2 words. Stuff like, I don't know, cheap, working, things like that. Well, those are just single words. I can perhaps do a better job if I'm not only counting words, but I count a sequence of 2 words. So things like so-so, well, that's 2 words. So maybe that's a feature that will lead me to better predictions if I'm also counting not just the words, but a sequence of 2 words called bigrams. And I can choose the bigram range in these vectorizers. In these vectorizers, I can choose the bigram range. So I'm going to do kernel and restart and clear output because I'm getting dangerously close in memory. So I got to be judicious about what cells I run, so my kernel doesn't crash. So it's going to be a little bit tricky, but I think we can do it. Restart and clear output, and it's not clearing it out, I don't think. It's probably lagging behind. And let's see, do I have internet connection? I may not. Let me just double check. Been plaguing me. I think I do. And my internet may not be stable, so just give me a sec. Okay, I think it should be back to normal. Okay, sorry about that. Okay, all right, clear things out. There's always a baseline 200 megabytes being used, which is very annoying. I don't know why that is the case. And let me go ahead and selectively run my cells. And I am good to go. Okay, I probably need this here. That's all I'll take for the meantime. Anything else, I will import it. Okay. So from sklearn, let's import my pipeline. If I need a pipeline, import pipeline. sklearn, let me go import compose, import my column transformer, From sklearn, I probably need a grid search. So model selection, import grid search CV. And from sklearn, a linear model, import ridge. So it's the same workflow I've been having before, right? In fact, I can probably just kind of copy and paste this here. Let me just go ahead and use the hashing vectorizer. Yeah, let me use the hashing vectorizer at first. I know it's a little bit faster. Do my grid search. Got my selector on review text. But with my vectorizer, I'm going to choose the n-gram range. So make sure I look at the proper documentation for that. If I look at that there, let's see. Where is it? N-gram range. There you go. N-gram range. N-gram range. And what I'm going to say, I want to count both words, which is 1 n bigrams. So I create my model. And I call it this normalized. Should probably call it bigram. Let's go ahead and fit my bigram model on data and ratings. I'm going to name error because I probably have a typo because it's called bigrams. Let me just make sure I've matched those two. Now I'm fitting my model. Let's see how long this takes here. Could I use Google Colab for running these notebooks? You could probably use Google Colab to run these notebooks. Keep in mind that you have to make them private because you'll be violating the copyright. But the other thing to keep in mind is that you'll have to make sure that you have all the packages installed on Google Colab. Most notably would be the grader, which you do not have available. So you can try to perhaps run the lecture notebooks and have some success in running those lecture notebooks, so long as you keep the content private. But something like the grader, unfortunately, you won't be able to run and connect with. Okay, so any questions about this Q3, right? It's basically what we've been doing before. It's just now we're including bigrams as features. Any questions? Why are we using the default range as 1 and 2? We're not actually, why are we using default? Actually, the default range isn't 1 and 2. If we look at the documentation for the hashing vectorizer, what we realize, and I can't do tab autocomplete because it's running, so what I can do is I can just look at the documentation on the site, scikit-learn, hashing vectorizer. Actually, the default is 1 and 1. So we're not using the default range, the default value. So 1 and 1 would mean, okay, we want to count words and words, right? So that's why it's just 1 and 1. If we want to include both words and bigrams, it's 1 and 2. If we just want to include bigrams, it's 2 and 2. Notice it's taking a while to train. It's taking a while to train because there are more features. There are more features involved, so it's going to be slow to train. Any other questions we want to bring up? Well, that ran. Let's see what score we get. Ah, not too bad, right? First stab at it, and I get a score of 1 over 1. Not too bad. Didn't have to tune hyperparameters. Did not even have to tune hyperparameters. Any questions we have about Q3, right? It's basically what we've been doing with Q1, Q2. Nothing too exciting, pretty boring. Q4 is a more exciting question. Any questions about Q3 before we move on? We might be able to wrap up this mini project already today. Okay, I'll take that as no, but do let me know. Do let me know. Now, Q4 is the more interesting question of the bunch. I'm going to delete my screen here. And let's talk about what's going on. 4 candidates are basically alpha. Oh, yeah, we choose multiple alpha values. Oh, yeah, I forgot. So we are tuning it. Yeah, we're only choosing 4, right? We're only choosing 4. And are basically, just the alpha values. Yeah, so I was wrong. We are actually tuning our model, but we're doing a rather coarse grid. Just choosing 4 different alpha values. So best params, 0.3 was the best value. 0.3 is at the edge of my grid. So let's do this properly, right? Let's do this properly. If 0.3 was my best answer, that's the edge of my grid. Well, let me expand my grid that way. So that's what I'll do here. I'll expand my grid that way. Let's try 0.1. Notice I'm using a coarse log space. I'm using a rather coarse log space. So let's try that. And let's see if we come up with a better result. Since we're doing bigrams, we use 2. Does that mean that n-grams we would use n in the range of? Yes, correct, Esau. If I wanted to include words, bigrams, and trigrams, a sequence of 3 words, I would use an n-gram range of 1 and 3. 1, 3. Exactly. So in fact, I can kind of flesh that out here. When n-gram range is equal to, let's say, 1 and 1, just words. N-gram range of 1 and 2, words and bigrams. N-gram range of 2 and 2, just bigrams. And n-gram range of, let's say, 1 and 3, this is words, bigrams, and trigrams. For example, this product was. That's a sequence of 3 words. So that'd be 1 feature we'd get out. But at this point here, we're going to blow up in our dimension. As we go through 3 different feature, a sequence of 3 words, there's so many combinations. There is really so many combinations of 3 words, right? Just so many features we generate that we probably would not have a good model. We probably would lead to overfitting. We might even be able to train the thing because there's just way too many features out there. So let's see if this ran. This is still running, so let's see what we come up with there. So it's a little summary of different options we have here. Frankly, you're never going to really do trigrams. Maybe there's something specialized for trigrams, but there's just way too many features. It's intractable. So it's more of like, are we going to include words or words and bigrams? That's 99% of the time, that's what we'd be asking. I wouldn't even look at bigrams until you really need more predictive power. One of the things I advocate people is build a simple model. Build something that works right now. It may not be the best, but it will always be a benchmark for future improvement. See how well it does. Increase the number of, include bigrams. Let's see how that translates perhaps to a better model. All right, that's still running there. So while that is running, I can go ahead into this whiteboard and explain what's happening with Q4. So we've been doing basically creating models and making predictions. But one of the things we could do is we can take these trained models that make predictions and understand what's going on in our process. And what we're trying to do is we're trying to find very polar words. For example, the word terrible is probably only going to appear mostly in negative reviews. The word terrible when it appears, will probably appear in negative reviews. The word like great, when it appears, will probably primarily appear in good reviews. So essentially what I can do is I can come up with the following probability. The probability of encountering a word given that it's a positive review. And the probability of encountering a word given that it's a negative review. These are conditional probabilities. The way you want to read the syntax, this symbolism, is this is a probability of encountering a word given. That vertical line means given in probability. Given it's a positive review. The probability of encountering the word, a given word, given that's a negative review. So for example, the probability of encountering the word terrible given it's a positive review. And the probability of encountering the word terrible if it's a negative review. So the probability of terrible given a positive review will be rather high, right? Because it's more than likely going to be in, negative reviews. This will be rather low. This will be rather low, right? The probability of encountering terrible given a positive review is kind of low, right? Yeah, there might be some positive reviews that use the word terrible, but not that much. The probability for me encountering terrible in a negative review will be rather high. So this ratio, what I can do is the way to come up with the disparity between these two probabilities, these two conditional probabilities, is to come up with the ratio. I can say the ratio of terrible given it's a positive review over encountering terrible given it's a negative review. I can compute this ratio and I can take the log of this ratio. And now my question to you is, do you think this, given our intuition about terrible and how the when terrible is used in reviews, do you think this ratio would be very large positive number or a very large negative number? What's your intuition? Given our intuition with the frequency of the word terrible in both positive and negative reviews, do you think this ratio would be rather large or rather negative? Very large positive number or rather large negative number? So the probability of encountering terrible for a positive review and the probability of encountering terrible in a negative review is rather high. So this ratio, much close to, not less than 0, very, very close to 0. So log of a number that's close to 0 is a very large negative number. So this will be rather large negative number. Large negative number. Yeah, we take the log of a number less than 1, we get a negative number. The log of a number less than 1 is a negative number. The log of a number greater than 1 is a positive number. So we understand this ratio should be less than 1. So it's going to be a negative number. And if that ratio is very small, very much less than 1, it's going to be a negative number. And that tracks with so that means that terrible has a large negative polarity. It's a polar word. In other words, when we encounter it, we primarily encounter it in one type of class over the other. Now let's look at another word. Let's look at another word. The word the. What do you think is the ratio, the probability of encountering the word the in a positive review compared to the probability of encountering the in a negative review? What do you think is this ratio? And let's not worry about the log first. Let's not worry about the log right now. What do you think, given your intuition for the word the, what do you think this ratio should be mostly about equal to? What do you think about what do you think about this ratio? Is it very much close, very much greater than 1? Is it less than 1? Is it about 1? What do you think? What do you think? What's your intuition here? Yeah, the word has a neutral connotation, right? The word the, right? You encounter the word the in a review. Well, you know, you don't really know if it's a positive or negative review, right? It's used throughout both positive and negative reviews. So this ratio should be probably close to 1. So the log of a number close to 1, right? The log of a number that is close to 1, yeah, and you are right. In your humble opinion, you are correct. This ends up being pretty much 0, and that kind of makes sense. A word that's common in both classes should have a ratio of 1, these probabilities, and it really isn't really a polarizing word. It's not really a polarizing word. So we get a ratio, we get the log of that to be close to 0. So that's what we want to do for this mini project, for this question here. For all the words we count, let's come up with the polarity score. And let's return to the grader the most polar words positively and the most negatively polar words. And that's what we're going to go ahead and do. And we're going to use the naive Bayes model, the naive Bayes machine learning model that learns these conditional probabilities. And this finished running. And it looks like 0.3 was still the best parameter. So it just so happened that in our previous grid search, 0.3 was at the edge of our grid and was the best. We expanded to larger values, and it just so happened that, yeah, 0.3 was really the best. But nonetheless, we did our homework. We have more faith that we properly tuned our model. And good job, we get a score of greater than 1. Okay, so we'll download the data set. And we'll delete some of past variables that might be clogging things up. And we're going to go ahead and let's see what we're going to do here. We're going to come up with the ratings of our data. So we actually have a separate data set that just has the 1 and the 5-star reviews, split apart. So we got to get the ratings. So for X in data polarity, we can say X, I think it was called, what was that key called? I forgot, but if I go back up above, it was called overall was the rating. Overall. Now we got the ratings. We got the rating, got a key error because I have a typo. Okay. And now let's start building my model. So let's see step process, right? I should perhaps write some sort of, let's see what it says. Right? Use naive Bayes, use TF weighting, remove stop words. Okay. Pretty straightforward. All right, so I'm going to create a model and I have my pipeline. So my converter to data frame, followed by my vectorizer. Column transformer. Vectorizer right there. Vectorizer. And my classifier, which would be a naive Bayes model. So let me go ahead and import that. Scalar naive Bayes, import multinomial naive Bayes. Here's my classifier step. There it is. There's my model. And I am good to go. Right, got to fit it. Got to fit my model. Data polarity and ratings. Well, that ran pretty quickly. And now I've got to pull out those conditional probabilities. If I look at the documentation, if I look at the things that I've got something called, let's see. Oh, because I got a pipeline. I can pull out my last step and call it dir. And I got something called, let's see if I find it here, feature log prob. Oh, those conditional probabilities are stored in that attribute, feature log proba. And copy that. Okay, well, let's look at the shape of this. What's 2 by over 250,000? Okay, well, let's try to rationalize that. Well, I have 2 classes, so that makes sense. I have 2 rows. Well, let's see how many features I have. Or I can probably look at my vectorizer, which was step 1. And that is, there's my selector, right? There's a selector underneath there. It's a little bit trickier to pull out. Let's see how I can pull out the step. I think I can get that via, let's see, name transformers. Okay, I want my vectorizer. So there's my vectorizer. Well, let's see how big the vocabulary is. Vocabulary. There's my vocabulary. Let me take the length. So what I've done is I looked at my pipeline. I pulled out the vectorizer. That's what I did there. Pulled out the vectorizer and looked at the vocabulary attribute, which is a dictionary that maps word to the index. And this is telling me that the length of that vocabulary is 257,015. And that matches up with the shape of this NumPy array. So it looks like this here tells me the log of probability of word I given class J. So exactly what I want to figure out here to do this polarity. Of course, it's taking the log of it already, but maybe I do some mathematical manipulation to actually come up with the polarity scores. So we'll work on that next week. Take care, everyone. Have a good rest of your day, good weekend. See you back here on Monday as we wrap up our mini projects for this course.